That's now the more and perhaps the most disturbing thing of all, they appear to have the ability to materialize and dematerialize without a trace. One of the great mysteries of the UFOs isn't seeing them, is trying to figure out where are they when you don't see them. Some people say, well, they're from another galaxy. Most physicists will debunk that for lots of reasons. They seem to pose that way, but for lots of, if they came, if there are that many coming from another galaxy, you'd think you'd sense the traffic. We'll come to some more reasonable explanations, and you're going to discover the two top researchers in the last century, really, is Jacques Vallée, France, and J. Allen Hynek, the American. Now, J. Allen Hynek was head of astronomy at Cornell, and he set out to debunk this nonsense about UFOs, and he became one of the most ardent, competent, balanced researchers in the trade. J. Allen Hynek, he died a few years ago. Those of you that saw the movie Close Encounters of the Third Kind, whether you realize or not, saw J. Allen Hynek because he was in the crowd. I was on a board in those days with Alan Adler from Columbia, and they had him as just a gesture appear in some of the scenes, just as an extra. And the Lacombe of that piece of fiction, of course, was patterned after Jacques Vallée, the Frenchman. Both of these respected researchers came to the conclusion that they're not intergalactic for lots of physics. There are a lot of physics rebuttals to that conjecture. They both argued that these things are demonic. Their term. They've written many, many books. You can check them out. These are not religious people. They're not people with any kind of personal agenda. But they came to the conclusion that these things, on the one hand, and by the way, we take for granted that we strip away the nonsense and the hoaxes, set that aside. There's tens of thousands of files you have to wallow through. When you cut through all that, there's still a core group, a substantial core group of real events that need explanation. And so on the one hand, they exhibit physical properties on the one hand. On the other hand, they also violate all physical laws. And so the conclusion that both J. Allen Hynek and Jacques Vallée and others have come to is that they're hyperdimensional, that somehow they come from another dimension periodically. That causes us now to stand back a little bit and do a little tutorial on hyperspaces. And we're going to get into why we feel that the Bible is an authenticated message of extraterrestrial origin in the first place. So let's talk a little about hyperspaces. There are only two kinds of... A hyperspace, by the way, just a term for a space of more than 3 dimensions. You and I are familiar with two-dimensional space. It's called a scratch pad or a photograph or a piece of paper is a two-dimensional representation of something, typically. Three-dimensional space we're familiar with because we live in it, and we also build models in 3 dimensions. We probably have a vague feeling of a 4th dimension called time. We don't get too comfortable with that unless you've done some special study, but we sort of acknowledge that reluctantly. Hyperspaces, frankly, is just the term used to study spaces of more than 3 dimensions. And we discover there's only 2 kinds of people that can really relate to hyperspaces. And that's mathematicians with special training and small children. Okay? Because they haven't, their prejudice has been blindfolded, so to speak. Now, the one book that is second to the Bible in its publication, all of us know the Bible is the most popular book in the history of man, but the second to that would be Euclid. And that's where most of us have been taught in school. And most of us, when we went to school, had trigonometry or plane geometry, same subject in a sense. We all know that a triangle, if you add up the angles of a triangle, adds up to how much? Anyone? 180 degrees, you betcha. So if I have a 30, 60, 90, it adds up 180. If I have a 45, 90, in fact, any triangle, if I add up the angles, it would add up to 180. Suppose, though, that my partner and I went out to a large field here, and we very carefully laid out with the transit a very large triangle, and when we got back with our figures, we added up the 3 angles, and it added up to more than 180 degrees. What would you conclude? That we'd messed up, huh? No, what have we encountered? Anyone? The curvature of the earth, exactly. See, if you take a course in navigation, one of the things that you'll have to get some background in is spherical trigonometry, where you can have a triangle with 90 degrees in each corner. And so, see, this little rule that we all learned, that a triangle, by implication, a plane triangle, a flat plane, adds up to 180 degrees, that's only true for a universe of 2 dimensions. So when you find that rule violated, it's a hint that you've encountered an additional dimension. And Dr. Einstein made history with that insight, because he was grappling, of course, with the nature of space, and he realized that length, mass, velocity, and time are relative to the velocity of an observer. In 1915, he generalized that, basically discovered that there's no distinction between time and space. And perhaps the most important thing from the general theory of relativity, we won't get in the math, of course, but is to realize that time itself is a physical property. You and I do not live in 3 dimensions. We live in at least 4. In fact, we now discover much more than that. But this idea that Einstein recognized as he grappled with the properties of space, that there's an additional dimension required, and he went to 4 dimensions to resolve the time issue. And his theory of relativity has been confirmed over 12 different methods to over 14 decimals. So it's no longer really a theory. It's well-accepted basis in certain fields of science. So when we need to go beyond Euclid, which of course deals just with 3 dimensions. And in June 10th of 1854, the most important lecture in mathematics was given by George Riemann. He invented a thing called metric tensors. And that tool that he developed proves to be one of the most profound tools in advanced physics. And it took over 50 years, in fact over 60 years, for Dr. Einstein to use that tool to develop his 4-dimensional space-time. And it's too bad that Einstein went to his death frustrated by not being able to solve certain problems, which if he had applied the technique going to 5 or more dimensions, they would have yielded. It took his successors to do that. Because in 1953, Kaluza and Klein both developed more than 4-dimensional models which integrated light and supergravity in a model. In 1963, 10 years later, Yang and Mills both developed what they call Yang-Mills fields, which reconcile electromagnetic and nuclear forces. That physicists are pursuing some way to integrate all that we know about the physical universe into a common model. And in as early as 1984, and it's still a current conjecture because there's still problems with it, but scientists now generally believe that you and I live not in 3 or 4 or 5, but in 10 dimensions. And if you read in this area, you'll encounter superstrings and such, and we have briefing packs on this for those that want to get into it more. The point being, we need to understand that the 3 dimensions you and I are familiar with are not all there is. There's more. Let's imagine you and I can't move up. It'd be futile for me to try to communicate 4, 5, 6 dimensions to us to get together without having more mathematical tools. But what we can do is we can go the other way, and it may stretch our horizons here a little bit. You and I are 3-dimensional beings. Let's imagine a 2-dimensional world. That would be like a large tabletop or a large flat plane. Now, let's imagine that 2-dimensional world populated by 2-dimensional people. You and I could come along and poke our finger through the plane of their existence. And what would they see? They would see a circle. They'd only see that which they could relate to in their universe. But if we as a 3-dimensional being are putting our finger through that 2-dimensional universe to the 2-dimensional people in the 2-dimensional universe, they would simply see a circle. Well, in fact, let's imagine that a ball fell through that 2-dimensional universe. To the 2-dimensional observer in that 2-dimensional universe, he'd see from nothing to a point. It'd grow to a large circle, and then it would shrink back to a point and disappear. He wouldn't be able to relate to what happened because he doesn't have the insight of that 3rd dimension. You with me so far? Now, if you had some other kind of a shape, say a tumbling cube, it also would go through, and it would take odd shapes as it passed through and then disappear. So one of the problems we have, suppose you and I are going to try to communicate a 3-dimensional object to that 2-dimensional world. How would we go about it? Well, there's a couple of ways. One would be to do what an architect would call projection. For example, if we had a cube, we could, in effect, shine a light that would give you a profile of that in 2 dimensions. And you discover very quickly that that works, but it's not too useful in letting the 2-dimensional person understand a 3-dimensional cube. So there's another way you could do it. You could take a 3-dimensional cube and you could unravel it. You could take it and just unfold it and lay it out, and that would be a way to communicate to this 2-dimensional person what this 3-dimensional cube is like. But you'd quickly discover as you tried to do that, his understanding is likely to be incomplete. You say, Chuck, what's all this got to do with anything? Well, let's talk about a 4-dimensional cube. That's called in mathematics a Hinton cube, and there are such things.